throughout this work whenever required. So basically, I'm going to talk about supersymmetry and why we are using the non-perturbative approach initially, and then we are going to jump to supersymmetric quantum mechanics. I'm going to talk then about the hybrid Monte Carlo technique, then various superpotentials that we have used in our work, and what are the results that we have got from it, and some the conclusion and way forward. So let's just start with the supersymmetry and non-perturbativity. So let's start with supersymmetry. What is supersymmetry? What are we expecting? So supersymmetry, we say, is a principle in which for each particle in the standard model, we are actually predicting a super partner. For example, for boson, we are looking for super partner with fermion super partner, and vice versa. So and the spin as both fermion and boson, that must differ by half the integer. So the exact unbroken supersymmetry, in that case, we'll have particle and its superpartner will have similar mass. But in case of broken supersymmetry, we see that we can have superpartners of different masses. But as we all know that it's a beautiful concept, but unfortunately we are not able to get any sort of results in this particular case. Is there any question? Okay, so we know that this is a beautiful theoretical idea, but nature is certainly not supersymmetric. So all the discussion regarding the supersymmetry is actually, are there any question? I'm hearing any sounds, please. But we know that nature is actually not supersymmetric. So all the discussion that keeps revolving around supersymmetry is actually around the broken supersymmetry. So instead of just having no supersymmetry at all, it's better to talk about broken supersymmetry. So let's just go to the spontaneous symmetry breaking. What we say is that the equation of motion, or the Lagrangian, that obeys symmetries, but the lowest energy vacuum solution, those do not exhibit that same symmetry. But in the dynamical supersymmetry breaking is also part of spontaneous symmetry breaking. In the symmetry breaking, we say that that supersymmetry which is broken spontaneously, such that it is supersymmetric at the tree level, but the breaking that actually is these non-renormalization theorems, we say that if the supersymmetry is actually unbroken at the tree level, it means that it stays unbroken to all the orders of the perturbation theory. So the only way the dynamical supersymmetry breaking can occur is because of the non-perturbative effects. So there are various sort of non-perturbative approaches that people use, and here we are actually using the lattice technique. So the non-perturbative framework that we have actually used here is that we are studying the supersymmetric theories on lattice. We are discretizing the supersymmetric theories in most of the cases we have fixed as one. The we have In most of the cases we have imposed the periodic boundary conditions. The lattice size is such that it is actually one in a way that the lattice spacing and the number of lattice sites, those goes opposite. If we are increasing the number of lattice sites, the lattice spacing goes on decreasing, and at the end what we are actually looking for is like taking the lattice spacing goes to zero limit and get the target continuum theory that we want to actually study. But yeah, while applying these theories on lattice, there are certain issues. Whenever we apply these theories on lattice, the fermion doubling issue is an issue we will talk about more in the next slides. There are other issues also. As the fermion doubling is there, supersymmetry will be broken also. On lattice, Leibniz rule also do not work. So there are some sort of issues, but how are we tackling those issues, and what we are doing, we'll see in how we have approached our results, we'll see in the next slides. So let's start. Next is the supersymmetric quantum mechanics that we have worked with. So simply supersymmetric quantum mechanics is the application of supersymmetry algebra to the quantum mechanics, and it started with Edward Witten's 1980s work around the supersymmetric quantum mechanics. It actually started off like a base to study supersymmetric quantum field theories on lattice, only the supersymmetric quantum field theories, but it was easy to actually study the supersymmetric quantum mechanics, and then in a it became a field in its own, a vast field in its own. And Witten also introduced index that we call as Witten index. If we relate it to the supersymmetry breaking, for a spontaneously broken supersymmetry, Witten index is equal to zero, though not vice versa. We'll talk about it. But Witten actually gave this idea of supersymmetric quantum mechanics at that time. And yeah, this is just a toy model, involving bosons and fermions, and we studied various properties of the theory involving bosons and fermions in supersymmetric quantum mechanics. Is like the base for us to go in higher dimensions with gauge and all other things. The continuum action, I'm going to talk about the what is the continuum action we've taken. Supersymmetric quantum mechanics. On 1D we have this. We have taken the temporal. On lattice we have taken the temporal, like discretization of the temporal part. So what we have? We have bosons. Those are linked with each other. Potential. So W prime is the first derivative of the superpotential with respect to field phi. And these but this particular action and the fields that we have here, the above action is actually invariant under two particular supercharges, namely q and q bar, and they follow the certain algebra. They anti-commute with each other, sorry, uh, with itself, the both the supercharges. And when we actually integrate out the auxiliary field from this particular action, we can integrate out it by finding it's the only equation of motion for that particular field, and the action changes its form. So the action is reduced from this equation 1 to equation number 4. Now, how the supercharges convert bosons into fermions and vice versa. This is the particular way how they act on phi and psi's and psi bars. So, by using these things, we can actually prove that both Q acting on S and Q bar acting on S in the continuum gives us zero. Though in the discretized version, both will not uh, actually be zero. Only one will satisfy that particular thing. But in continuum, we actually say that Q acting on S and Q bar acting on S should be equals to zero. So again, the how the lattice discretization thing that has happened, that we have discretized a 1D lattice by putting the theory on it, such that the lattice sites are equally spaced with lattice spacing A, and which is equal to T inverse in most of the cases whenever we are taking beta to be 1. In certain cases, we have actually also imposed the antiperiodic boundary conditions. In that case, we are varying everything, like we are also varying the lattice size in that case, just to have a zero temperature limit. We'll talk about it when the results will come. Okay, so now let's discretize this particular action. So we have discretized this action on a lattice. The derivatives now are replaced by, like, uh, symmetric backward or forward difference operator that is in our hand. Actually, what do we want to take, whether we want to take the forward derivative operation, backward, or the symmetric one. And m here is actually the fermionic operator. W prime again is the first derivative of the superpotential with respect to field. Index I and j are representing the lattice sites. But we know whenever we are actually putting the supersymmetric theory on the lattice, the fermion doublers of that breaks supersymmetry. So how to get rid of the fermionic doubling, and why is it happening? Let's just get a brief look at it, that why is it happening and how we can get rid of actually that. So when we actually trying to put naively trying to put the fermions on the lattice, we encounter fermion doubling. So it's actually like whenever we are taking the continuum limit, the fermions the fermions are behaving as continuum fermions. Fair enough. But whenever we are actually at the brilliant zone boundary, whenever we are writing the propagator in terms of like momenta, and whenever we are on the brilliant zone boundary, those fermions actually behaving all or also behaving as the continuum fermions. um, Whether we any component of the momentum part is like on the brilliant zone boundary, those fermions are actually behaving as the continuum fermions. So instead of one fermions, we are actually getting 2 raised to power d fermions. This is the fermion doubling issue that we get. So how to get rid of it? So in our particular case, what we have done is like replacing the mass with the Wilson mass matrix. So Wilson mass matrix, here we have m delta ij, and the second part actually solves the thing for us. And also,
Navdeep,
yeah.
can you please explain what do you mean by a continuum fermion? Is it in terms of its momentum or something like that?
Yes, actually, like that. Whenever we are writing the fermionic propagator, that is actually in terms of the lattice spacing at that point of time, and the momentum components. So when we take a tending to zero, fermions are behaving in a certain way. But also at the brilliant zone boundary, those fermions are actually behaving similar way as a tending to zero limit fermions are behaving. That is what I'm trying to say at that point of time, at that part.
Okay, and also you said that for the lattice, we assume that the spacing between each lattice point is equal.
Yes.
And how we ensure that point?
So the way we actually write our code, or I mean, the theory is as such that we take a lattice and we divide it into equal parts. We need to make sure that actually.
Okay, but there must be a condition which we put
Yes, yes,
on that.
yes. The lattice spacing is same, and it is such that the way we are increasing the number of lattice sites, the lattice spacing goes on decreasing. Means size remains the same, but as number of points on those sides will increase, the spacing between those points will go on decreasing.
Okay, okay. Thank you.
So with this, actually, the symmetric operator that we have taken, that also introducing doubling in the bosons. So that all both bosons and fermions are actually having doubling in that particular case. So we can actually have forward or backward difference operator instead of symmetric to just avoid the bosonic doubling. But for the fermionic doubling, we are introducing the Wilson mass matrix. That this term is actually killing that particular doubling happening in the fermions part. So this removes actually both the doubling if present in the fermions that is there, and if present in bosons also, this will get rid of that. But also for to put fermions on lattice, we cannot directly put the Grassmannian fields on the lattice. That is because the exponential of the fermionic minus fermionic action part, that is not positive definite. What that does is that the important sampling is somehow not that good, and the results, the measured quantities, we cannot actually trust those results. So how to simulate the fermionic sector on the theory on the field? We actually replace fermions by pseudo fermions. So what we do is like we integrate out the fermionic part, we get the determinant of m part, and we replace it by the pseudo fermions. By doing so, our action is updated in a sense. Instead of m, we can take actually m transpose m due to certain conditions that we there are certain reasons behind this, that we it's easy actually to solve this m transpose m. matrix that we are getting is actually diagonal kind of matrix, and it's much easy to solve this particular equation than only M inverse. So this M transpose M inverse chi part, we need to solve it using certain techniques. We can use gradient descent, or we can use conjugate gradient. Conjugate gradient in a way is more faster as compared to gradient descent. So we used here conjugate gradient algorithm, technique of hybrid Monte Carlo. I'll not talk much about it, but a small segment about it. So it actually contains two particular parts: a deterministic part and a non-deterministic part. Firstly, we evolve the fields with the help of molecular dynamics, and at the end, we perform a test whether to accept a particular configuration or to reject the evolved configuration, that we call as the Metropolis test. So for the evolution part, for to conjugate phi and chi, we are taking the momentum conjugate p and pi, and our total Hamiltonian contains those momentum parts also. So when then we actually evolve, as I said, evolve all the fields. I've just written some of the fields here. Initially, we actually take the momentum, both the momentums from a Gaussian distribution, and then evolve it with the help of these leapfrog equations. Um, at the end, we apply again, as I said, the non-deterministic part, Metropolis test. We evolve it and check whether to accept this particular thing or reject this configuration. So with hybrid Monte Carlo, we actually try to make sure that the acceptance is around like 60 to 80 something is like a good estimate for acceptance that we want to take. In Menati's talk, there was one question about detailed valence equation, that why we are using this detailed valence in Monte Carlo. So I just wanted to comment one thing on it. When I was going through like literature, this I found interesting, that for Monte Carlo algorithm to converge to the correct equilibrium distribution, that is important here, that we are actually looking for a particular equilibrium distribution. For that, uh, our algorithm should be ergodic. Ergodic in a sense that like in principle it should reach any configuration in the phase space. And why detailed balance is required, in a sense that we need to have a stationary distribution, uh, so that we actually get the thermalized value. Thermalization part in Monte Carlo is like always important. So to get the thermalization part, to get thermalized results, we need detailed balance in Monte Carlo technique. Uh, so yeah, let's now move to the main section of my talk. That what do we need? Before that, some supersymmetric probing tools that we have used. We have checked word identities, that whether word identities are satisfied or not. And the other things that we have checked is mask gaps, the ratio of the mask gap, the fermionic and the bosonic. If it is like nearly equal to 1, we say that supersymmetry is preserved. If it is not equal to 1, we say that there is supersymmetry breaking effect there. And also in the literature, one interesting part that we saw, that the total the expectation value of the total lattice action, that should be nearly equal to the number of lattice sites. So what we saw in supersymmetry breaking, whenever there is supersymmetry breaking, uh, that total action actually goes away from the number of lattice sites. Fermionics behaves as number of lattice sites by 2, but the bosonic lattice action in that case is like less than what is actually required in that case. So we are starting with even and odd superpotential that we are taking. So the superpotential is of the following form: M is mass and G is coupling here. So on lattice, as I initially mentioned, that instead of mass, we'll taking the Wilson mass matrix toward the problem of fermionic doubling. So by putting that and using the form of the Wilson mass matrix, our first derivative of the superpotential looks as equation 18. Fermion matrix here is actually important, because in certain cases what happens is like fermion matrix is not positive definite always. So what that does is like, we can typically call it some sort of sign problem happening when the fermionic matrix is changing sign in the simulation. Sometimes it's positive or negative. In that particular case, we can actually not trust our results. So we need to make sure. In this case, we know M is positive, G is positive, so we are actually getting all the fermionic matrix is always greater than zero. That is positive definite. But in certain cases, when we are going to take odd superpotentials, we need to make sure that that thing happens. So I'm not going to talk about the odd superpotential. It will just have degree 5 instead of degree 4, the highest power. So I'm going to start off with the comparison of the even and the odd superpotential. This is the action. The figure that you are looking at, we have shown two actions, normalized action, normalized to the lattice sites. So these particular two actions, if we see the blue dots that we see is for the even superpotential. In that particular case, the normalized lattice action, the value of the normalized lattice action is nearly equal to 1 for all number of lattice sites. But in case of the odd superpotentials, the value of normalized lattice action is not equals to 1. Though you can if you go to like number of lattice sites are increasing, we are actually seeing that it might converge to one, but that's actually not the case, because this particular action is a normalized action. And whenever we are normalizing it, say first point is for like 8 lattice sites and the last point is for 64 lattice sites. So the actual difference from that total number of lattice sites was increasing. Here we can just because we have divided, we are normalized it, it looks like it's approaching to 1. But the difference actually from that particular action that was posed, as we can see in like degree 4 superpotential, that difference was slowly increasing in a way. So yeah, so this was the first result that we saw, which suggested that the degree 4 superpotential somehow like supersymmetry is preserved, but in degree 5 superpotential, it's actually not the case. Second thing that we checked is the mass cap ratio, bosonic to fermionic mass cap ratio. So how we find this both bosonic and fermionic mass cap ratios? These mass cap ratios are actually extracted from the correlator functions. So both bosonic and fermionic correlator. The bosonic correlator was I have not included in it, was a form of like cosine fit, and the fermionic one was like decaying. So in if we fit like first half of the lattice sites to an exponential decay function, we'll see we'll like extract the physical bosonic and fermionic mass caps. I mean, we'll get the lattice one and we'll convert it to physical. So the left figure is for like degree 4, the right figure is for degree 5. So in degree 4, we can see that the ratio of both fermionic and bosonic mass caps, of bosonic and fermionic mass caps, is approximately equals to 1. But in case of degree 5, it's not the case. So another evidence which showed that the even superpotentials, those have supersymmetries preserved in those, and there is supersymmetry breaking in case of odd superpotential. And the final and the last thing that we have checked is actually the ward identities. Um, we are not seeing that much of effect in this. How the ward identities are found, actually, it's after clubbing the correlation function, the bosonic and fermionic correlation function, and just adding and subtracting those correlation function, we have got two ward identities, namely W1, W2 in these figures. So what we saw is like the left one is for 64 lattice sites for degree 4, and the right one is for degree 5. But yes, we can actually see more or less the difference between both. That on the left we see that um, let's just check the center part between, like, say 20 to 40 lattice sites. That in that particular space the word identities are beautifully like satisfied. On the edges there are lattice artifacts, so we are actually not getting word identity satisfied at the edges, but we are actually looking at that plateau part, and that plateau part is more or less supersymmetry is preserved, but not that is not the case with the odd degree superpotentials. Okay, so but again, there are some in literature. People actually say that whenever we have supersymmetry breaking in certain cases, the partition function and the Witten index in that case vanishes. Witten index we have previously we have discussed about that the Witten index, if the supersymmetry breaking is there, the Witten index is actually zero. But if the partition function in that particular case is zero, the observables that we are getting, we actually cannot trust. But in our simulations, there were no such instance of runaway behavior of observables. Um, there, there is more to discuss on that. We'll actually get back to that some again sometime. But we can account it somehow with the Monte Carlo simulations that we are getting. Maybe the randomness in the Monte Carlo simulation is actually not making the partition function completely zero, and we can somehow trust our simulations more or less. In the work Arpit did, that is put on archive recently also, with complex line join, there was not much runaway behavior that we saw in that case also with the supersymmetry breaking thing. But still, just to make sure that our results are correct, we went ahead with the anti-periodic boundary conditions. So when we impose the anti-periodic boundary conditions, the lattice size that we call as beta, which is also the inverse temperature in that particular case. So also varying a and t, and in this case we have to vary beta also, such that we at the end we can say beta is very high, say going to infinity, and temperature going to zero limit. We can see whether the supersymmetry breaking is there or not, because with temperature there's certainly supersymmetry breaking effects there. For all the values of beta, these are the values of the extracted mass gaps, the ratio of the mass gaps. With all the values of beta, the left one is for 0.5, then middle one for 1.0, and the right one for beta 2.0. For all these beta values, we saw that they were supersymmetry breaking. I mean, the ratio was, as we were approaching the continuum limit, the ratio was going away from that particular one value that we were expecting. Uh, but to be more sure, again, we checked the action, and that actually showed us much better results. With the action, we can see that as we are increasing beta, that we are decreasing the temperature. In that particular case, we can see that the expectation value of action, the normalized expectation of value of action, that should be 1 in supersymmetry preserved case, that is actually going away from that particular that is more like a solid result that we can say, that actually says that their supersymmetry breaking is there in with odd superpotential, odd degree superpotential case with the antiperiodic boundary condition, though we actually proved also with the periodic one. But just to make sure that our those results are correct, there is no runaway behavior because of vanishing Witten index and all these things. We went ahead with the antiperiodic boundary condition, and we saw the similar results. The other superpotentials that we discussed was the very first one is the scarf superpotential. So with the scarf, superpotential is it is actually used in a sense that just to check our simulations where the code is correct or not, because we know that there is supersymmetry is preserved in this particular case, and that is shown beautifully by these two results of the word identities that we are presenting here for 32 and 64 lattice sites. The word identities are satisfied in the plateau region that we expect. So uh, supersymmetry is preserved in the scarf and superpotential case also. Next come is the important one, PT symmetric superpotential, the more focus at the end that we give our focus on. So PT symmetric superpotential derivative should be of the following form. uh, it contains minus iota g iota phi 1 plus delta. So the values of delta that we can take is like greater than minus 2. So we can take all the values of delta greater than minus 2, but for Monte Carlo to work fine, we had to take only a subset of values, subset of delta values. In a case when the superpotential is actually real, so the total action is also real. So we took the values of with delta like 0, 2, and 4, as we can only take values of greater than minus 2. So the rest of the values, if we're going to take like 6, 8, and 10, those are going to give us similar sort of results. With 0 and 4, 0 works as something like free theory, because the fermionic, that the matrix, that part where which clubs of bosons and fermions in that, the mixed part is not there in the action anymore with the 0. With the 4, we get some results. With the 2, 2 is an interesting one, because in that particular case we are actually getting the negative coupling case of the even superpotential that we are actually the previously discussed. So with these PT symmetry cases also, we need to take massless theories, but on lattice we need to take mass. We cannot simulate our theories without mass. So what we did for the case with delta 2 and delta 4, we simulated it for different mass values, and then at the end we took the mass going to zero limit. So full analysis, as I just said, for all the particular values of delta, with even the odd delta values when the superpotential is actually complex. In that particular case, Monte Carlo cannot work, but complex Langevin certainly can work. So that full analysis is done in a recent work by Dr. Nosh and Arpit. So you can go and check that out also. Okay, so let's start with the delta zero case. Now here the tool that we have taken to probe supersymmetry, whether supersymmetry is preserved or breaking is there, is the mass gap ratio. So here it's clearly, we can see clearly as we are increasing the number of lattice sites, that is we are decreasing the lattice spacing between the lattice sites. We are approaching the continuum also, and the mass gap ratio that we are getting is nearly equals to 1. So that shows us that supersymmetry is preserved in this particular model. The important one then is the delta 2 case. Huge error bars, but still, I'll come back to that why there are huge error bars and all. So when actually we extract the mass gap value from the correlators, those mass gap values are like not the physical values, those are the lattice values. So when we actually convert those particular mass gap values into the physical one, we need to convert multiply it with certain factor, and that factor in this case is the number of the lattice spacing. So say we have 64 lattice spacing. In that particular case, there the value of the error bar actually increases a lot. So and more or less, maybe next time whenever we are going to do it, the finding of mass gap from the correlator, instead of the exponential decay, we'll try out certain other methods which are there in the literature also. So but it's more or less clear in this particular case that for all different values of m, and then for all different values of lattice sites, and at each lattice sites we worked with different values of m, and then took m tending to zero limit and checked the bosonic and fermionic mass gap ratios. um, those ratios were more or less within certain error equal to 1. With delta equals to 4 case, uh, again we saw the similar sort of trend. We worked out with like different values of uh, masses for each value, each different lattice site, and then extrapolated those to get mass equals to zero limit, and again check that the mass gap ratio in both the cases and in all the cases as we are approaching continuum is more or less equals to 1. So with all these 0, 2, and 4 delta values, we completed a particular subset that was required to say something about whether supersymmetry is preserved or broken in that particular case, and we come to the conclusion that BT symmetric superpotential supersymmetry is actually preserved. For other cases also, like for delta 1 and delta 3 are with simulated those models with complex line join, and similar sort of results are there also, the paper which I mentioned just a few slides back. So more or less I am done with all the talks. So let's summarize what we have got. So we say that HMC, the hybrid Monte Carlo on lattice, is actually an effective tool in studying supersymmetric quantum mechanics, as we have seen, though there with some limitations to the PT symmetric cases. But in coming time we might look to like improve that particular Monte Carlo so that we can simulate the other sector that is left where Monte Carlo is actually not working. The results that we have actually got is like supersymmetry is preserved with in even degree superpotentials, the scarf one superpotentials, and PT symmetric symmetric superpotentials. But supersymmetry is broken in case of odd degree superpotential. So these were more or less the results that we have got. Way forward in this particular case is like maybe adding gauge to it. There are like one or two plans, like going ahead with PT symmetric superpotentials in higher degree to validate our results. As in literature, it has been said that PT symmetric superpotentials, there is supersymmetry is preserved in those cases. In the so we might want to look at in some higher dimensions also, and maybe adding gauge to it and studying in like metrics models. That is also a direction we are looking at. So certain references that I'm going to quote here is our paper and Arpit and Sir's paper. The basic paper is Witten's 1981 dynamical breaking of supersymmetry, and Simon and Gregory's paper for which laid this work in like early 21st century, or should I call it 2000? I don't know. So and some other papers also which people has actually studied this work in some other way for some other models. So yeah, thank you. I'm open for questions. I think I've ended 15 minutes early. Yeah.
Okay, if there is some question or comment, please go ahead.
If you take a superpotential which is something like sinh phi,
Yeah.
sin
Mhm.
phi, which is so that W prime will be even, right?
So
Then, so that means W is odd.
mhm.
Then would you get breaking like
Yeah.
tan phi W prime equal to tan phi is odd, right? So that means W is even.
Yeah. So, in a sense that we can say that all these sort of superpotential that you're quoting, we can actually write these superpotential or these terms, sines and sinh in exponent. Sorry, in the polynomial form, and whatsoever polynomial form is there, say it is odd, we'll observe supersymmetry breaking, and if that particular polynomial form is even, we'll actually end up with the preserved supersymmetry case.
No, but they have infinite or they're transcendental functions. So, I mean, you mean to say the lattice kills the higher degree terms? You only have to worry about the dominant terms. You
I'm
checked
actually,
it for 5 to the power of 5, but
yes.
what about 5 to the power of 201? Are
Uh,
you sure that that will be subdominant?
More or less, I think I'll say that I'm sure that I'll work that out also, but I'm more or less sure about it that with 5 raised to power, like say 201, there should be like supersymmetry breaking.
No. So that's not, I'm saying that because the transcendental function, that Hamiltonian
Charan,
thought.
yeah, it can be done, Charan. It can be done. So Navdeep, maybe you can bring back that scarf one superpotential. It has some tan or something, no?
I was coming to that. Yeah.
So I mean, these type of functions we can include. It's okay. We can.
And you'll be able to check for even for transcendental. Since you've checked it for tan phi,
So this
it
can
should
be
not be that hard
this
for
can be any well-behaved function. We can check that on the lattice. Yeah.
You don't have to convert it to a polynomial.
No, there is no need for that. Yeah, we can directly use this.
Okay.
Any other questions or comments or something?
Okay, so if there are no questions,
Navdeep,
Yeah,
Navdeep.
yeah.
So in the PT symmetric case, so you took the limit this mass going to 0.
Yes.
So how did you fit it?
This was linear fit actually.
Okay, so is there some relation between these energy gaps versus with the mass in the superpotential? This m physical with this energy gap with the mass parameter. So is there some relation that you could?
As far as literature is concerned, I haven't actually found any certain evidence for like when is it linear or something. But just from the results perspective, what I saw was that in both the cases, delta 2 and delta 4, the relation is actually linear in this particular. But I remember in like the 0 dimension case that you did, it was linear sometime and it was not linear also, right?
So that was the alpha, that was the twist field in
Twist
the
parameter.
x-axis. Okay, thanks. So other was like in the anti-periodic boundary conditions, so they support the periodic boundary condition results.
Yes.
Okay. Okay, thanks.
are there any more questions? So I think there are no more questions. So thank you, Navdeep, for such a nice talk. I have one announcement that this meeting was our last meeting of this semester, and the next meeting will happen on January. So yeah, then we will end our section now.